This is the Math 140 lecture number 16 on percent change and compound growth. The first example says an investment increases 12% one week, then drops 9% the next week, and finally increases 20% in the last week. What is the return on investment, which is the same as finding the total percent change, and what is the weekly compound growth rate? So the first thing, you might naively think that you could just add these together as pluses and minuses, and that's not correct. But if you did that, this is what it would look like. You would get, let's say, obviously a 12% increase, and then let's say you recognize the drop is 9%, and then finally 20% increase. If you combine those, that's what, 32 minus 9 is 21. Actually, that's 23. 12 minus 9, that's 3 plus 20. Okay, 23. So this might be something that somebody would imagine is the way to handle it, but this won't be the right answer. It's not an overall 23% change. I'll show you what it really is and why that's the right answer. Another thing that's kind of puzzling about this is it doesn't say what the starting amount is, and it doesn't need to say the starting amount. It wouldn't matter what that starting amount is. The answer would turn out to be the same regardless of whatever amount you started with. And so actually what we could just do is just say let A0 be the starting amount. And if I'm looking for the percent change, it's the same as the return on investment that I was doing in lecture 15. Just say percent change. It's the change in the quantity divided by the original amount. And so what I could do here is think, well, we need to figure out what the new amount is, subtract what the old amount is, and then divide by the old amount. And it doesn't matter what that new and old amount actually is numerically. We have enough information to be able to answer this. So in a process, just like what I was doing before, I could calculate that new amount by looking at these increases and decreases. So that percent change, I'm going to try to figure out what that future amount is after 3 equal periods of time here, and those periods of time are weeks. So we could say if you started with the initial amount and increased it by 12%, actually let me back up. Just to spell everything out, I think I'll put plus 0.12 because of the 12% increase. And then, because there's a drop of 9%, I'll do 1 minus 0.09. This is essentially, what I'm doing is saying 100% take away 9%. So it's minus because of the drop. And then it finally increases 20%, so we'll have 100% plus 20%. And all of this is calculating the new amount. So then we would still have to subtract the initial amount. We divide by the initial amount. So in order to find the percent change, I have this A0 1.12 times, this is 0.91, and then 1.20 minus the initial amount, everything divided by the initial amount. So again, you can skip this step, because if you realize what's going on here, I have a 12% increase, a 9% drop. A 9% drop means 91% of whatever we had before. So in the second week, you get 91% of what you had because of the 9% loss. And then in the third week, there's a 20% gain over whatever you had in week 2. And so I'm multiplying by 1.20 because it was a 20% gain. Right? Now, at this point, if you see the algebra, this A0 quantity can just factor out and cancel with the denominator. As I move on to the other examples, I won't even write this step because it happens every time. And we can start to speed things up, but just to explain what's happening in those later steps, there's going to be a minus 1 here because I'm factoring out A0, the initial amount, and that initial amount won't matter. So this is how I can calculate the percent change. I just recognize there are 3 equal periods of time. The first period we have a 12% gain, then we have a 9% loss, then we have a 20% gain, and we're just minusing 1 because we have this minus 1 here that's left over when we factor out that initial amount. You could even think of this as if you had actually started with $1, then this would be the new amount, or what was the, yeah, if investment was worth $1 at the start, then this would be the new amount, and then we would minus the original dollar, and then we could divide by $1 to get the percent change. Typing all that in, you get about 0.22. It's not exactly 0.2, say 0.223. So we could say 22.3%. So it's close to that estimate that I had made, but this could vary a lot. I mean, the fact is that what really happened is that the overall investment increased 22.3%, not 23%. That could make a huge difference if the initial amount was, $1 million or several $1 million. That 1% is a lot of money. Okay, so I've now concluded that there's a roughly 22% overall gain in this investment after going up 12% and dropping 9% and going up 20%. Overall, it's increased 22%, and that's the return on investment, which is mathematically the same as finding that percent change in the investment. But there was another question here. We're asked to find the weekly compound growth rate. And there would be another very easy mistake to make if somebody took the answer that we just got, 22, and divide by 3. This isn't right. This will give you the wrong answer. If I did 22 divide by 3, that's like 7.3, and so that's a naive and wrong, but it's an estimate perhaps, but it's not the true compound weekly growth. If you grew by 7.3% every week, you will go well above 22% overall. So if it isn't 7.3, if this is the wrong way to do the calculation, well then what is the right way to do it? Well, the compound growth rate is the same as this rate of return that I was doing in the previous lesson in lecture 15. To find the compound growth rate, it's the same as the rate of return. We could call this the compound rate of return or compound growth rate, and so that means we need to figure out the final amount, divide by the initial amount, and we need to have equal periods of time. And so n is number of equal periods of time. Well, we just found the future amount already in this example. We recognize, actually, I'll just do it one more time in the way that I did it. We had an increase of 12% here. Right? We had an increase of 12%, then a drop of 9%, then an increase of 20%. And so that right there, this whole thing, this is the future amount. A 12% increase, a 9% drop, and then a 20% gain. And that's it. That's the A sub n. And we divide by the initial amount. And how many equal periods do we have? 3 weeks. 1, 2, 3 increments. So that's 3. And that will be, because those were weeks, this will be the weekly compound growth rate. And minus 1 is part of the formula. And of course, you know these A zeros are going to cancel. So we don't really have to write that in all of the remaining examples, because you realize algebraically it doesn't matter what the starting amount was. And I still remember from just the first part of this calculation that this was roughly 1.22. Let's say it was 1.223. So I'm taking the cube root of that number minus 1. That's 0.069. So that's about 6.9%. And that's definitely different than the idea of taking the 22% overall change and dividing by 3. Right? It's really growing on an average weekly compound rate of growth of 6.9%. Let's move to number 2. It says enrollment at a college increases 10% one semester, increases 7% the following semester, then drops 15%, and finally drops 5% in the next 2 semesters. So what's the percent change in enrollment and the average growth rate in the enrollment? And once again, you can't just add and subtract these together because they are compounding each percentage on previous enrollment levels. And so that's exactly what this lesson's about, is this sort of like overall percent change and compound growth rates. So it's precisely the same math as what I had just done in example 1, so I'll go a little bit faster with this one, and I'll just say that we could start with any level of enrollment, and it won't matter what any numerical value of enrollment. It won't matter. The answer will be the same. What we'll do is we'll just say, just take the 10% increase. Another increase of 7% means I'll do 1.07. That's the 7% increase. I got the 10%, got the 7%. It drops 15% in the following semester, so you have to look at that as a 1 minus 0.15. And finally drops 5% in the last semester. Sometimes when I'm explaining this, I actually go a little slower than that. I do this. So you can see how an increase of 10% tracks to this factor, and then an increase of 7% is here. A drop of 15% is here. And finally a drop of 5% is here, and then each of these I'm simplifying. Now what I'm doing here is subtracting 1, because that is essentially the overall procedure for getting these percent changes, right? To take the future amount minus the initial amount, divide by the initial amount, where we're not even given the initial amount, it would cancel out. You're basically just getting all of these compound growth and loss factors, and then just minus 1 to get the overall percent change. Just like that. So in this example, this is our percent change. And typing all those in, you get about negative 0.05. Let's round it off. Negative 0.05. So negative 5%, roughly. Now just to compare, if we had taken a 10% gain followed by a 7% gain followed by a 15% loss and then a 5% loss, how much does that add up if you just combine those together? That's 17 minus 20, so that's negative 3. So you see that's giving me a different result that just isn't accurate, in the sense that because these are compounded changes on previous amounts, this is really the true change overall in the enrollment. It's a 5% loss, roughly 5%. I rounded off, so rounded it to the nearest whole number percent. Now, again, this says what is the percent change in enrollment and the average growth rate in enrollment. Well, the actual growth rate, we can see it's got to be negative. It's actually gone down overall 5% over these 4 semesters. It isn't correct to take that 5% divide by 4. What we're really doing is equivalent to finding the rate of return. Generally in finance, it's this compound growth rate, and if we're looking at equal intervals of time, then that's the value n in our formula. So let's do compound growth rate, and we could just take this amount as the future amount, and then you have to be careful when you type this in the calculator, because this whole thing has to be multiplied together, then raised to a power 1 over n, in this case 4, because we have 4 equal periods of time. And to get that compound growth rate, it's minus 1 to see what the growth rate is compared to 100%. Typing all that in the calculator. Maybe I should type that in on the screen here, just because we do have to be very careful about multiplying all these together, then raising to a power 1/4. So it would look like this. Do 1.1 times 1.07 And then I can close parentheses there and say raised to a power 1 divided by 4. And again, make sure that you're getting the 1/4 in the exponent. If your calculator is not putting it in the exponent, you need to get another pair of parentheses for that. Now if I just type the whole thing in, I can just do -1 here. And I get about -1.3 if you round off. Well, -0.013, which is -1.3%. So what we're calculating is that the enrollment has dropped 5% overall, and it has dropped 1.3% on average each semester. That is the growth rate, a negative growth rate average. So dropping by 1.3% each time, 4 times in a row, gives you an overall 5% drop. We could call this the per semester compound growth rate, but of course that growth rate is clearly negative, and it means there's an average loss of 1.3% each semester in the enrollment. In fact, this is done, but we could check that. So to check to see if that really makes sense, or to once again kind of reinforce the principle, suppose we started with, let's say, 1,000 students. We could now calculate if we lost 1.3% 4 times in a row, what would be the final amount? It should be 95% of what we had. It should represent that overall 5% loss. So starting at 1,000, using this rate here of -1.3%, it's actually -0.013 that I need to use, and if we did that 4 times in a row, what's the future amount? That works out to about 949 students. So what is the percent change? It's that new amount minus the original amount divided by the original amount. So I can see we've lost 51 out of 1,000, and that's about -5%. So that's checking. That's the per semester compounding growth rate that is, in this case, lowering 1.3% every semester, that contributes to an overall 5% decline in 4 semesters. Okay, number 3, subscribers to a YouTube channel increase 5% in one day, 8% the next day, and by 20% the following day. What's the total percent change and the daily compound growth rate? Well, you can't add 5 plus 8 plus 20. That's what, 33%. This is not right because we're looking at these compounding increases on previous increases, and so the right way to get that is just as we were doing before. The percent change is a 5% growth, 5% increase, 8% increase, and then that 20% increase. And I'm minusing 1 because that's sort of like our initial 100% of what we had divided by 1. So what does this come out to be? 36.3608. Let's round off, roughly 36. 36%. Right? So by just adding those percentages, you get 33, and that's just wrong. It's actually a 36% overall increase. It really wouldn't matter what order those occur, because you can see multiplying them in any order is going to give you the same answer. So that's actually an important point. The order didn't actually matter, but the fact that it's increasing by 5% means that that following 8% is larger than, if it hadn't increased previously, right? So these are compounding, and that's the effect of compounding. You don't just add them together, you compound it, and you get 36% is the overall total increase in those 3 days. And then again, you don't divide that by 3. We have 3 days here, but if you divide that by 3, you get 12%, and it's not going up 12% a day on average. What is it really going up? What's the average daily growth rate here? We can take that 1.36 that we got as sort of like the future amount, take a 1/3 power because we got 3 equal periods here, minus 1. You could imagine, let's say that you had started with 100 subscribers, right? And then you'd have 136 after 3 days. And then if you divide by 100, the original amount, you'd be right back to this 1.36, right? So I'm skipping all that work and just saying all you need is to multiply those factors together. 1 over n, where n is the number of equal periods, minus 1 part of the formula. What do we get here? About 0.108. So 10 or 11%. Let's say it's 10.8. So it's not 12%. 12% every day for 3 days is going to beat that 36% overall. This is really growing at a 10.8% roughly daily increase. Average compounded daily increase of 10.8% produces an overall increase of 36%. Okay, last example, number 4. Sales for an online retailer increase by 10% in the first month, then by 8% in the second month, by 3% in the next month, and by 5% in the last month. What's the total percent change in sales? Well, this is just what we've been doing before. We can do this one faster. 10% increase, 8% increase, 3% increase, 5% increase. To get the percent change, minus 1. 28%. Roughly. Of course, it always depends on in the directions, whether it says how many decimal places to write. Didn't specify here, so this is a reasonable place in the context here to round off, say roughly 28% overall increase in sales. You can sort of see that, if you added 10 plus 8 plus 3 and 5, this is actually 18 plus another 8. That would be 26. So it's this continuing compounding that means the overall growth is higher than we would have guessed by just adding those numbers together. This is 4 periods, and if we just divide it by 4, we'll get 7, but that's not the answer, right? Of course, the answer here is the monthly compound growth rate. We'll do it like this. We'll take all those values. Actually, I kind of already know this is going to be, well, I'll say it like, I'll write it out. So it's 1.10, 1.08, 1.03, and 1.05. Technically what you're doing is that's the new amount, that's the original amount. Whatever the future amount is canceling, right? And what we have here are 4 equal periods. So be very careful about typing that correctly into the calculator to make sure you multiply all these together and then raise to a power 1/4. And then subtract the 1. It's about 0.065. About 6.5% monthly increase to get a 28% overall gain. Next question says, if sales were 75,000 units initially, what is the sales level after the given 4-month period? So what I'll do here is take that initial 75,000, look back at my gains, 10% gain, 8% gain, 3% gain, and a 5% gain, and figure out where we are. That's about 96,360. Let's say if these are units, we could round off here, 96,362 roughly. Now of course I would get the same thing if I just took 6.5% 4 times in a row. It's the same thing. So this is the answer, but you could do 75,000 and increase by 6.5% 4 times. Now it may not be exactly to the number because I rounded off here, but let's see what we get. Well, it's a little hard to see there because if you actually type that in, you're going to get 96,484, and that makes you pause. Wait, those are definitely not the same. And it really is because this is rounded off. So that was just rounded off too much to after those 4 increments to really expect this is close but not the same, and it really is all because of rounding. So if I really want to hit that same value, I just need to be a little bit more accurate. So if you go back to where I was here, it wasn't really 6.5%. It was more like 6.466, something like that, 6.4. So if I'm a little more accurate, 6.4, right? If I go back and look at this value, this was more like 0.06466, and I had rounded it off. So if I go back and use that value, 6.466% increases each month for 4 months, roughly 6.5. But if you want to hit that number exact, we need to be more accurate on this value. This is, well, let's see. Yeah, that's it. 96,362 if you round off. So yeah, 6.5% every month is very close. It's a approximate to the to the average growth rate. 6.466 is a little more accurate. Yeah, okay, so that's that. I mean, if you're wondering, either way is correct, and there isn't anything here saying specifically how many decimal places. So if you had used this value, if it ever came down to sort of test questions or homework questions, you could use this rounded off value, you could use that value, or you could do it the way that I just did that. These are all correct. They're all a matter of where we choose to round off. And if we round off, we're going to have slightly different results. So we hit about 96,000 unit sales after those monthly increases. So how long does it take to reach 150, let's say, to double? Now this is really not actually specifically the Math 140, but I thought it might be just interesting to add in here. This is where we need the log function. So what we're looking at is an equation, and it might be convenient here just to say, if you started with 75,000 and you expect 1.065, approximately 6.5% gain each month, how long until you double? So really I need to figure out what that variable is there. And of course I've rounded up. This is optimistic, hoping that it really is 6.5% increase every month. How long until you hit that 150,000 level? So we could divide. So solving for x is something that we don't really actually do when it's in the exponent here in our Math 140, but it's a good thing to know how to do. To solve for the exponent, that's when you need the log function. And the first thing you'd have to do is get rid of this factor before you take the log. So let's divide both sides by 75,000. That way these can cancel out. We have 1.065 to the power x equal 2. So we're trying to figure out what exponent 1.065 to what power will give you 2, and that answers this question. So you could take the log base 10 or the ln, because it doesn't really matter what base we use. So let's just take ln. We're doing the natural log of both sides. It's the property of the ln that allows us to put the x in front. So it looks like this. That's the ln of 2. So x is the ln of 2 over the ln 1.065. I mean, I'm doing this because it's sort of an obvious question, right? If you could see something growing at 6.5% every month, how long until it doubles, or any other value, right? So this is just some basic algebra that, the application of these log functions, they're on the calculator. You might wonder how you use them, so here it is. So type that in. Isn't really in our homeworks or tests, but it's a good thing to know how to do. This is about 11. So, yeah, maybe in about a year it'll hit 150,000 if it continued at that 6.5% rate. Another thing that comes up a lot in this context is very often we'll switch to, rather than compounding every discrete number of times. Discrete means like individual. We could just, it's a very common thing to do to model growth, particularly in like, biology, with a continuous compounding model. So this question just says, what's the equivalent continuously compounded growth rate? So what I'm talking about here is, if you compounded continuously, what rate would you compound continuously that would give you the same 6.5% monthly? So answering that is, continuous compounding uses this base E. I'm trying to figure out what power for a base E gives me that same growth of 6.5%. So here, definitely want to do ln because it's already a base E. So you can do ln e to the x is ln 1.065. So here, the ln of e to the x, this is just x. These are inverse functions. So we're looking for the natural log of 1.065. This is about 0.063, let's say. 0.063, rounding off, so 6.3%. So the conclusion is, if you compounded continuously at 6.3%, you get the same effect as 6.5% every month. This means compounding continuously at 6.3% produces the same overall growth as monthly compounding at 6.5%. Alright, so that's the end of this video. I hope it's been useful and interesting and helpful.